Camera is a sensitive detector of light. Accurate measurements of light at its different parts of the spectrum are at the heart of all natural sciences and medicine. They offer important information ranging from biomedicine to exploring the universe. The most sensitive light detectors are based on superconductors. Superconductors help us take detailed pictures of the universe and help us discover the secrets of the cosmos, such as the cosmic microwave background, dark energy, Big Bang and cosmic inflation. Superconductors can also be used for smaller tasks. In X-ray imaging, they allow us to perform a very accurate elemental analysis. And for terahertz, they can be used to measure body temperature variations to accuracies of fractions of a degree from the infrared light emitted by the body. Improving the cameras further might allow us to identify molecules in X-ray spectroscopy and use terahertz detectors to measure protein dynamics. Such progress requires creating new detectors with improved sensitivity and capability for creating large detector arrays. Most detectors used today are based on measuring how the electrical response of the device changes under minute temperature variations caused by the absorbed light. This requires the presence of probe pulses sent to the devices to measure the response. However, the probe makes the device more complicated and adds noise, which hampers resolution. Because of this, it would be desirable to create a situation where the absorbed light directly drives a current whose detection then signals light detection. In other words, we need to create a similar functionality as in photovoltaic cells used in solar panels, where the absorbed sunlight creates electrical power. But there are a few issues. First, we have to make it work with far smaller amounts of light. Second, it needs to work at temperatures within fractions of a degree above the absolute zero temperature to yield the ultimate precision. This is the challenge in the SUPERTED project. It is not easy to create directionality to the charge current. Semiconductors in photovoltaic cells freeze out at low temperatures, so they cannot be used. In metals, current is not a function of the voltage, and hence light that corresponds to alternating voltage leads on average to a vanishing current. Superconductors often used in detectors have the same problem. But, based on our theoretical finding, we noticed that by combining superconductors with ferromagnets, we can solve the problem and create unidirectional current. We need a combination of two properties in particular: magnetic proximity effect into a superconductor from a nearby magnet and spin polarized tunneling. To make the unidirectionality work as a sensitive detector, we need to combine superconductors and magnets in an optimal thin film geometry. This requires the use of modern sample manufacturing tools. Finding the optimal recipe is not easy and has required a lot of trial and error work. In San Sebastian, we have a custom system that uses techniques of surface science, such as photoelectron spectroscopy, scanning probe microscopy, and surface diffraction. In combination with techniques available in the synchrotrons, for example photoelectron and X-ray absorption spectroscopy and spectrum microscopy. Everything in the ultra-high vacuum environment. These are needed to develop and optimize the fabrication process that later on will be reproduced in conditions more relevant for medium and large-scale production. The result needs to be assessed by measuring the electrical characteristics at sub-Kelvin temperatures. Then the devices are processed into detectors that couple to the desired spectrum of light and measure the light-induced current. After preparing the samples in San Sebastian, they are sent for electrical and thermal characterization in Pisa, Italy. This characterization needs to be done at millikelvin temperatures, requiring sophisticated measurement techniques and expertise. During the project, we have managed to find the recipe for creating the desired unidirectionality of the current. The operation is similar to ordinary semiconductor diodes that are key elements in modern electronics, such as radios and computers. However, the new superconducting tunnel diodes work at ultra-low temperatures and for much smaller signals than their semiconductor analogues. They can also be used for other tasks and may become important in quantum technology. This was an unanticipated but important byproduct of the detector work. Creating detectors requires still further steps. The light needs to be coupled to the devices. That is why we have manufactured antennas for coupling terahertz light into the devices and absorbers to absorb the X-ray radiation. Realizing the whole chain is a complicated optimization procedure. The infrared detectors are shipped from Pisa to Grenoble, France. hosting one of the world's best test systems for measuring minute amounts of infrared light with superconducting detectors. Whereas the X-ray detector samples are prepared and measured in Jyväskylä, Finland, with its unique X-ray setup. The results are analyzed by theorists working in San Sebastian and Jyväskylä. The Finnish Advocam company based in Espoo provides expertise into developing the detectors into products. Now we are ready for the first demonstrations of SUPERTED detectors. With better detectors, who knows what we can see?